Okay, picking up where we left off, we have calculating Keq and using it, which will be coming up. Normally, you're going to use either concentrations in molarity or partial pressures in atmospheres. And you need those values, again, at equilibrium, not initial values. And if you're given those values at equilibrium, then that's pretty easy. If you're not, then that might require some work. But once you have those values, then you just put them in the equation for the equilibrium constant and you get your number out. So a really easy example here is this equilibrium between N2O4 and NO2, where you have one N2O4 in equilibrium with two NO2s. If the pressure of N2O4 is 1.74 atmospheres and the pressure of NO2 is 0.512 atmospheres at equilibrium, then what would be Kp? Well, this is nice. You've already been given the equilibrium concentrations in terms of partial pressures, so you just stick them in the equation. The equilibrium constant expression for this reaction in terms of, partial pressures is going to be partial pressure of product, which is NO2 squared, divided by the partial pressure of the reactant, which is N2O4, to the first power, because there's the coefficient here is 1. So that's going to be 0.512 atmospheres squared over 1.74 atmospheres, and that's equal to 0.151. And another thing, some chemists argue that equilibrium constants should have units, and others argue that they shouldn't. And for the time being, anyway, at the moment, the side that says there shouldn't be any units for equilibrium constants are winning, and so we don't use units for equilibrium constants. Enjoy it while you can. This is one of the few instances in chemistry where it's actually acceptable not to write down any units. Normally that's a no-no. So using Keq as a formula just means, for instance, there may be cases where you know the Keq for a reaction, because they're, like I said, they never change for a given reaction at a given temperature. So there are places where you can look up values for equilibrium constants for certain reactions at some certain popular temperatures like 25 degrees Celsius. You can actually go to a book and look up the equilibrium constant for a reaction. And so you know that. And then maybe some of the equilibrium concentrations for some of the substances involved in the reaction, but there's one you don't know. So what you can just do is set up the equilibrium constant expression and solve for the thing you don't know. And that's what we're doing here. We have the reaction 2 SO2s plus O2 is in equilibrium with 2 SO3s. The equilibrium constant in terms of concentrations is 1.7 times 10 to the 6th at 700 K. And since they don't say anything else about that temperature during this problem, you can assume that the temperature doesn't change. So everything else is at the same temperature during this problem. And it says here, if the equilibrium concentration of O2 is 2.1 times 10 to the minus 3 molar, and the equilibrium SO3 concentration is 3.8 molar, what would be the equilibrium concentration of SO2? Okay, so Kc is just going to be SO3 squared over SO2 squared times O2. SO2 is the thing you don't know, and when the thing you're solving for is on the in the denominator of a fraction, you can just switch it with what's on the other side. So we get SO2 squared is equal to SO3 squared over Kc times O2. But of course, you want SO3 to the first power, not SO3 squared. So you take the square root of everything. And that will be the square root then of SO3 squared over Kc times O2. And then you just put in the numbers and take the square root, and turns out that the SO2 concentration at equilibrium is 0.06360. Okay, so not too bad. It's mostly just algebra. You can also use KEQ values in ways that are quite similar to the way we used, the way we used Hess's law for finding information about reactions where we don't know something. And so if the chemical reaction has changed, then the KEQ expression has to change with it. And the value of KEQ will change also. And so you can use known KEQs to find KEQ for a reaction where you don't know it. And some of the examples of what you need to do if you're going to alter a reaction would be if you're reversing a reaction, then KEQ is inverted. That is, you take 1 over the original KEQ. And it's demonstrated here, or proven basically, that if A goes to B, or A is in equilibrium with B, but it's written with A on the left and B on the right, so that you'd read it as A goes to B. The KEQ for this forward reaction, it will be concentration of B over concentration of A. Okay, simple enough, product over reactant. If you reverse that reaction, then B is now the reactant and A is now the product. And so the KEQ of reaction number 2 is A over B. And that is the inverse of the KEQ for the first reaction. So that makes sense. If 2 or more reactions are added together, okay, if 2 or more reactions are added together, then the KEQ for the overall result of that addition of reactions is the product of the KEQs of the individual reactions. So in this case here, if reaction 1 is 2A goes to B, the equilibrium constant for that reaction would be B over A squared, the product over reactant to the power of its coefficient, right? If you then add to it the reaction B goes to C, the equilibrium constant for that is C over B, again, products over reactants. If you add those 2 reactants together, you get, notice the B's cancel, 2A goes to C. The overall K you would expect for that reaction would be concentration of C over the concentration of A squared. Products over reactants to the power of the coefficient, right? Well, you can also get that expression by taking K1 times K2, because K1 is B over A squared. So you write that. And then K2 is C over B. So you write that. Notice the B's cancel, and you get C over A squared. In this case, that was really easy. All we had to do was basically look at the final reaction. We can come up with the expression for the equilibrium constant. But there are going to be cases like this where you're doing this with numbers, and you don't really need to know that it's C over A squared. You need the number for that. And again, the way to find it would be take the number for K1 and the number for K2 and multiply them. You've got the number for K3 if you're adding the reactions together. If the coefficient of the reaction is multiplied by, if all of the coefficients, I should emphasize, all of the coefficients of the reaction are multiplied by a number. And of course, you'd have to multiply all of the coefficients by the number, because if you only multiply some of the coefficients by a number, then you're going to throw the reaction out of balance. So assuming you're multiplying all of the coefficients by a number in the reaction, KEQ would be raised to the power of that number. So if you double all the coefficients in the reaction, the KEQ for that new reaction will be the KEQ for the old reaction squared. And you can just see that here. If A goes to B, then the KEQ for that reaction is going to be B over A. If you double both of the coefficients and have 2A going to 2B, then K2 is going to be B squared over A squared, and that is B over A squared, or in other words, K1 squared. If you took, say, the first reaction and cut the coefficients in half and had 1/2 A producing 1/2 B, then K for that reaction would be B to the 1/2 power over A to the 1/2 power, which is the same as B over A to the all to the 1/2 power, which is K1 to the 1/2. So that's actually fairly straightforward. And again, that can be used to help manipulate reactions and put reactions together so that they add up to another reaction. And then you just multiply the KEQs together and you get the KEQ for the new reaction. An example of that is this one here where it says, an example of that is here. But first, we'll just write the KEQ for each reaction and show how they're related. So in the first reaction, we have 2 N2s plus O2 yield 2 N2O. Okay, the KEQ will be N2O squared over N2 squared times O2. 2's really don't want to show up on this camera. Okay, times O2. And that will be KEQ for reaction 1. In reaction 2, you may notice that we've cut all of the coefficients in half. So now it's N2 plus 1/2 O2 yields N2O. So now KEQ will be N2O to the first power over N2 to the first power times O2 to the 1/2. And so reaction 1 is just reaction 2 doubled. And so what that means is that K1 will just be K2 to the second power. And sure enough, if you take KEQ for reaction 2, that's N2O over N2 times O2 to the 1/2 power, and square it, you get N2O squared over N2 squared times O2. All right, now in an example of how you can use that information to actually find the KEQ for a new reaction whose KEQ you didn't know, would be if we take this situation where we have NO, nitrogen monoxide gas, and 1/2 Br2, and that yields NOBr gas. And the K for that reaction, which is reaction number 1, is 1.41. There's another reaction by which NOBr can decompose to its elements, and that is quite a bit more likely to occur. And in that reaction, you have 2 NOBrs decomposing into N2 and O2 and Br2. And you can tell that this reaction occurs to a much greater extent than the first one, because the K for this reaction is 1.05 times 10 to the 30th power. The K for the first reaction is about 1. K for the second reaction is a little bit bigger. So this is an example of a reaction that almost goes to completion. There's going to be very little NOBr left once this reaction comes to equilibrium. And so what we want to do here is calculate the KEQ for the decomposition of nitrogen monoxide to its elements. So that reaction is 2NO yielding N2 plus O2. Okay, and so if you look over the first 2 reactions, you'll notice that this reaction, reaction number 3, is just reaction 1 doubled plus reaction 2. So once we double reaction 1, I'm going to call it reaction 1 prime because it's been changed. And that will be 2NO plus Br2 yields 2NOBr. Now that we've changed this reaction by multiplying everything by 2, we have to square the K1. So K1 prime is 1.41 squared, and that's 1.9881. Reaction 2, we used just the way it was written, and so its K value can stay the same, 1.05 times 10 to the 30th. And when we check to make sure that these two reactions really do add up to the reaction we want, we find that we have a Br2 to the left of the arrow in the first reaction and a Br2 to the right of the arrow in the second reaction. So they cancel out. And we have two NOBRs to the right of the arrow in the first reaction and two NOBRs to the left of the arrow in the second reaction. So they cancel out. And all you have left is two NOs yielding N2 and O2. And that is exactly the reaction we wanted. So now that we've got these two reactions to add up to that one, all we have to do is multiply the equilibrium constant values for these two reactions to get the equilibrium constant for that one. So K3 is equal to K1 prime times K2. And it got a little messy here, but remember K1 prime is 1.9881. And then that'll be times 1.05 times 10 to the 30th. And we end up with K3 being 2.09 times 10 to the 30th power. So this reaction also goes almost to completion too. Sorry. The next topic is reaction quotient. And the reaction quotient is also a very useful tool for determining whether a reaction actually is at equilibrium or not. You may put some reactants together in an equilibrium reaction and let them sit together for a while, and then come back later and measure their concentrations and see what they are. But you may not be certain whether that reaction is actually at equilibrium yet or not. And so what you can do is take the reaction quotient. The reaction quotient, or Q, is set up exactly the same as the equation for KEQ, except that the concentrations you're using for the reactants and the products may or may not be equilibrium values. So we're kind of questioning now whether we're at equilibrium or not. So you're going to use the concentrations, whatever you happen to have at the moment, and see if the ratio of products to reactants gives you the equilibrium constant. And if it does, then you're at equilibrium. And if it doesn't, then you're not at equilibrium. Okay, so essentially what happens here, and so we're comparing the value of Q to the value of KEQ. And essentially what happens in an equilibrium reaction is when you put the reactants for an equilibrium reaction together at first, you've got nothing but reactants and zero products. And so if you try to take, say, a reaction quotient at that moment by taking concentration of the products over concentration of reactants, the number is going to be zero because you got no products yet. So products, zero. And zero is in the numerator, that makes the whole thing zero. So essentially Q starts out at zero when you first put the reactants together, and it gets bigger and bigger and bigger as time goes on because you're producing more and more product and using up more and more reactants. So the numerator gets bigger and the denominator gets smaller. And so Q gets bigger and bigger and bigger until you get to the point where Q is equal to the equilibrium constant. And in that case, you're at equilibrium and the concentrations normally won't change anymore unless you change the temperature or dump something else in or something like that. But you can also approach equilibrium from the other direction. You could put the products in with no reactants. And like I said, a situation like that where you have all products and no reactants is essentially a situation where Q would be infinity. So it's very big because, you know, the concentration of reactants in the denominator would be zero. And as time goes on and you use up some of the products in the numerator and you generate more and more reactants in the denominator, that number for Q will come down if you're moving backwards. But again, once you get to equilibrium, the point where Q is equal to KEQ, then it stays that way unless you disturb it somehow by like changing the temperature or something like that. So if Q is less than KEQ, the reaction has not yet reached equilibrium, and it will go to the right until equilibrium is reached. Or in other words, the forward reaction will go ahead until equilibrium is reached. If Q is greater than KEQ, like maybe you started out with nothing but products, then that means that the reaction has basically gone past equilibrium, and it will run backwards or to the left until equilibrium is reached. And then once equilibrium is reached, then the concentrations won't change anymore. And if it turns out that Q is equal to Keq, then that means those concentrations that you put in actually were equilibrium values, and the system really is at equilibrium. Okay. So we're getting near the end of what I had prepared for today. An example of that would be a situation where we have a reaction occurring at 400 Kelvin, and Kp is, that is equilibrium constant in terms of pressures, is 41 for the reaction where N2 and 3 H2s produces 2 NH3. Notice we get yet another value for the equilibrium constant because we're doing the same reaction at yet another temperature. Okay, so we want to find Q in terms of pressure when the pressure of nitrogen is 0.124 atmospheres and the pressure of hydrogen is 0.113 atmospheres, and the pressure of NH3 is 0.00682 atmospheres. And then the question is the reaction at equilibrium? And if it's not, which way will the reaction go until it reaches equilibrium? So Q is just going to be products over reactants. So that's P of NH3 squared over P of N2 to the first power times P of H2 to the third power, because the coefficient for hydrogen is 3. And that's going to be 0.00682 squared over 0.124 times 0.113 to the third. And you end up with the Q being, QP in this case, being 0.2599. Forget that, I put a 0 in by mistake for some reason. 0.2599. And in this case, K is 41, Q is 0.2599. That's quite a bit less than K. So we're not to equilibrium yet. The reaction is going to keep running to the right, or the forward reaction, in other words, will run until you get to equilibrium. And that at that point, QP will be 41, just like KP is. But we're not there yet. Okay. So hopefully that makes sense. The next section, I'll give you a little preview here, is about using ICE tables. What ICE tables are, first of all, what ICE stands for is initial change and equilibrium. And we use ICE tables in cases where maybe we have the initial concentrations for some things involved in an equilibrium reaction, but maybe we only have the equilibrium concentration for one of those things. Okay, so like in a case where, say, A plus 2B yields 3C plus 4D. And the initial concentrations for everything, we'll say, will be 0.10. And since this is an equilibrium reaction, there will be a change in all of these, but we will end up with an equilibrium concentration of everything. And, so we have to sort of find out what the equilibrium concentrations of everything else are going to be. So say with D, we start out with 0.1 molar, and we also happen to know that the equilibrium concentration of D is 0.05. Okay. So D went from 0.10 to 0.05 during, between the very beginning of the reaction and equilibrium. Okay, D is a product, so that, sorry, it should have gone up. Make that 0.15. Being a product, normally you'd expect the product to go up. So it went up to 0.15. So during the course of the reaction, D went from 0.10 to 0.15. that means the change in D was plus 0.05, because that's the difference between 0.15 and 0.10. Well, now that we know that, we can use the stoichiometry and the reaction to find the changes in everything else, because C is going to change 3/4 as much as D does. So the change in C is going to be 3/4 times 0.05. And that's going to be 0.0375. And that's going to be in the plus direction because C is a product also. B is going to change by 2/4, whatever D does. And it's going to be in the negative direction because you lose reactants and gain products during a chemical reaction. So it's going to be minus 2/4 times the change in D. And 2/4, of course, is 1/2. And so this is going to be minus 0.025. And the change for A is going to be negative because that's a reactant also. And it's going to be 1/4 of whatever the change in D was. So it's negative 1/4 of 0.05. And that is negative 0.0125. And now that we know the changes for everything, we can find the equilibrium concentrations for everything, because initial plus change equals equilibrium concentration. Okay. So 0.1 plus the change, which is minus 0.0125, gives you 0.0875. And B, for B, we had 0.1 minus 0.025. And so that's 0.075. And for C, we had 0.1 plus 0.0375. And that gives us 0.1375. And now we can find the Keq. This Keq is going to be concentration of C at equilibrium to the third times concentration of D at equilibrium to the fourth over concentration of B at equilibrium squared times the concentration of A at equilibrium to the first power. And so what this is going to be is 0.1375 to the third times 0.15 to the fourth, all over 0.0875 to the first times 0.075 squared. And so this is going to be let me find my other calculator since it's easier to do stuff like that on the other one. Okay, so 0.1375 to the third power is going to be 0.0025996. And that will be times 0.15 to the fourth power. And that gives us, for the numerator, for the entire numerator, 1.316 times 10 to the minus 1, 2, 3, 4, 5, 6. And then for the denominator, we have 0.0875 times 0.075 squared. And that is 4.922 times 10 to the minus 1, 2, 3, 4. Okay, so we have 1.316 times 10 to the minus 6 divided by 4.922 times 10 to the minus 4. And this comes out to be 2.674 times 10 to the minus 3. And that would be your KEQ. Oops, sorry, someone went off the screen. So there's your KEQ. And that's how you can find it in a situation. And there are other situations that we'll encounter, but this is one of them, where you know, say, the initial concentrations, but you only know the equilibrium concentrations for one thing. A special application of equilibrium constants will be the dissociation constants for weak acids, which we also did in lab. Ka is an equilibrium constant for the dissociation of a weak acid. And in that case, you will often know all of the original concentrations in the dissociation of the weak acid, but the only thing you'll know at equilibrium is the pH value. But from the pH value, you can get the H+ concentration. And from that, you can get the change in H+ concentration during the reaction. And from that, you can get the change of everything else. And so you can find the equilibrium concentrations that way, kind of like what we did here. So, you know, like for instance, pretend that D was the H+ ion and 0.15 is what we got from the pH value. A 10 to the negative pH turned out to be 0.15. And then this would be basically a Ka problem for dissociation of a weak acid. Okay, so, and we'll do that in more detail on Wednesday. So until then, I'll see you later.